So let's start the exercises next. This is the exercise 13.1.1 and here we have to prove theorem 13.1.4. So as usual, we are first of all going to see the statement of the theorem in brief and then we will start the proof. So this is the brief statement of theorem 13.1.4. We have two metric spaces x comma dx and y comma dy and a function f from x into y and a point x0 in x. Then we have to prove that the following three statements are equivalent to one another. If any one of them is true, then the other two are also true. Statement A says that f is continuous at this point x0. Statement B says that if xn is a sequence in the domain space x that converges to x0, then f of xn, which is a sequence in the range space y, has to converge to f of x0. And statement C says that if V is a subset of Y which contains f of x0 and is also open in Y, then there exists an open set U in X which contains that point x0 and such that f of U is a subset of V. We start the solution with this mention that to prove that these first two statements are equivalent, it's enough to mimic the solution to exercise 9.3.1. This exercise asks us to prove a similar result, but where the functions are real valued functions of real variables. Here the functions are more general between metric spaces, but otherwise whatever we did back there, we have already solved this, right? You can adapt that solution to this general metric space setup without much change. The structure of the proof will not be changed. The only thing is that in appropriate places you just have to change some things. We next prove that statements A and C are equivalent. So first we assume A, we are now going to prove C. That means we will now assume that V is a set like this and then show that such a U exists. So let V be an open set in Y containing f of x0. And that is why, because of the openness of V and the fact that V contains f of x0, there will exist a positive epsilon such that the ball centered at f of x0 and having radius epsilon is contained in V. You have to understand one thing, okay? I could have written a suffix dy here to indicate the metric and hence the fact that this is a ball in the space Y. But actually, if you are careful, you need not write those things. The fact that this point f of x0 is in Y automatically tells you that this ball is a ball in Y. So this will be entirely contained in this open set V. And now you use your hypothesis, which is that f is continuous at x0. So for this epsilon, there will exist a positive delta such that the distance between f of x and f of x0 as calculated using the metric in y, that is dy obviously, is less than epsilon for all x belonging to x whose distance from x0 as calculated using the metric dx is less than delta. So this is just writing what f being continuous at x0 means. That is, for any x in this ball, this is the ball centered at x0 having radius delta and obviously it's a ball in the space x. For any point x inside this ball, its f image is inside this ball, the epsilon ball centered at f of x0. Why? Well, that is because this is the condition for a point to be inside this ball. And this is the condition for f of x to be inside this ball. And that's why the f image of this ball itself is contained inside this ball. Because if you take any point x from here, f of x is inside this ball, that's why. And this ball, of course, because of this, this one, is itself contained in V. So f of this set, this ball, is contained in V. And finally, you note this. that this ball is obviously an open set in X and which also contains X0. Every open ball contains its own center. So this is your set U, which is open, which contains X0 and whose F image is contained inside V. So that means you have proved that statement A implies statement C. So A implies C, and next we assume C, and we will prove that A is true. That means F is continuous at X0. Now to prove continuity, we choose any positive real number epsilon. And we consider the ball centered at f of x0 having radius epsilon, ball in the space Y of course. Now we know that this is an open set in Y containing f of x0. So by our hypothesis, that means statement C, there exists an open set U in X which contains x0 and such that f of U is contained in this ball. This is our V now. Now U is an open set which contains the point x0. So the openness of U gives us a positive real number delta such that the delta ball centered at x0, this ball is of course in the space X, is entirely contained in U. Now next let X be any point in the space X whose distance from x0 is less than delta, calculated using the metric dx of course. I am not going to mention this thing again and again, okay, from context it will be clear. Then of course X belongs to this ball Bx0, delta. Now what can you say about X, seeing all these things? Note that since X is a point in this ball and this ball is contained in U, X is a point inside U, and f of U is contained in this ball, this other ball. So f of X will be an element in this ball. So we write that f of X belongs to this ball. But then this in turn means that the distance between f of X and f of x0 is less than epsilon. So finally you have got here what you wanted to get. For that arbitrary chosen epsilon, you have found a delta such that whenever X is a point from X whose distance from x0 is less than delta, then the distance of its F image from f of x0 is less than epsilon. And this is what continuity at x0 means. So F is continuous at x0. That means we have now also proved that C implies A. So that means the statements A and C are equivalent to each other. Combined with the equivalence of A and B, we find that all the three statements are equivalent to one another. So this is where the proof ends means the solution ends. Make sure that you really do that part, okay, where you have to prove that A and B are equivalent. You see if you understand how to adapt that previous proof in this general setup. If you find it difficult, you let me know in the comment section below.